Okay, let's get started here. So hopefully all of you got my message that I posted in the listserv yesterday. One of the things that we're going to do today is fill out this sheet that gives you 4 options for group participation on the project. So what I would like you to do is basically put your name into one of the 4 different options there. Just sign it. If you're doing option 1 or option number 2, it would be nice if you could also, let's say, circle the people that are in your group. If you happen not to be sitting next to the person you're working with, well, hopefully the last one of you who are in the group will go ahead and circle it. If you would like to make changes at any time regarding who you work with in the group, that's totally fine with me. In fact, if after class, maybe you need to talk to someone, to say, well, do you want to be in a group because you haven't asked them yet, we can make changes here, okay? Just I would appreciate that if you, at least right now, sign up for one of the 4 slots here. And so then after class, what I will do is those who are in option number 3, sign up for option number 3, I will try to find you a group. If you don't want to end up working with that person, that's okay too. It's just a way for those of you who maybe do not know a whole lot of people in the class could find somebody else to work with. It's going to be to your benefit to sign up. It's going to be to your benefit to work in a group. You don't have to, but it will be to your benefit. Because as the projects go throughout the semester, they will get longer and longer and longer. And also, for those of you maybe this is the first time you've encountered R before, well, it's helpful to learn a software package with someone else. So you can ask them questions. Okay, so I'm going to start this going around. Just please sign your name in one of the 4 slots. And then pass it to the next person. Okay. Let's see. Next thing. I want all of you to restart your computer now. If you already happen to have something up on it, you don't want it to disappear, well, restart your computer then at the end of class. But if I would appreciate it that you need to restart your computer sometime today. The reason being is because on all these computers, TIN, RStudio, and the newest version of R have been installed. But in order for them to actually appear to everyone who uses these computers, the computer needs to be restarted. So please restart your computer. Is it on? I know all the monitors are by default turned off, and there's an on and off switch in the lower right-hand corner. Okay. Now it seems like I wish people who installed these updates would automatically restart them because it would make things easier, but that doesn't happen. Okay, so then today we will probably finish, get at least very close to finishing chapter 1, and we will discuss project number 1 later today after we talk about a little bit more material. So are there any questions? Okay. We left off last time on page 141. So I want to review a little bit what we did last time, just real briefly. So we were working with this GPA data set. Where we were using high school GPA to predict college GPA. And the data itself is in the file gpa.txt, so ASCII text file. I can read in the data into R using the read.table function. So if I simply type GPA, I see the actual data set. Now, to actually now estimate then the regression model, the sample model, I can use the LM function, standing for linear model, where in the formula argument I specify my response variable separated from my predictor variable by a tilde. And I say, well, where's my data? Well, it's in GPA. I put then the results into an object called mod.fit. So let me go ahead and do that. If I want to see names of the items that are actually listed in mod.fit, I can type names mod.fit, and I see a list of the items that are mod.fit. So for example, if I say mod.fit $coefficients, I get B0 and B1 from our regression model. And if I wanted to see a summary of all the stuff that's in mod.fit, I can simply type summary mod.fit, and we get all this nice little output here, including, again, B0 and B1. Okay. So that's just a brief review. Page 141 then. I have some final notes regarding this particular example. First of all, as I've said, as all of you hopefully have found out, R is free. You download and install on your computer. But R is also open source. So you can see all the code that is used to create R if you want to. You can see all the code regarding functions that are inside of R. So for example, if I type simply LM, I get the actual function that is estimating my model. This is the actual code. Now, if you're a beginner to using R, this code is going to be quite daunting to understand. That's expected. But as you get more and more used to using R, you're going to see, okay, that's why this is done, this is why this is done, and so on. But the nice thing is that with R, there's nothing that's hidden. That if you want to know exactly how some computations are done, take a look at the code. That's it. Try doing that with SAS, SPSS, or whatever other software package you maybe have used in the past. So nothing's hidden. Go back here. Now, just as a reminder, if you ever get stuck on stuff, you're not for sure how to do something, don't forget to use the help. You can simply type help parentheses, LM in parentheses to see the help for the LM function, or you can search for it via help, HTML help, search engine and keywords. You can type LM. Okay? But there are many, many other places to find help regarding how to do stuff in R. In particular, one thing that you might find useful is this reference card, it's called, that has been developed that shows all the functions that are typically used with regression analysis. So this class is called Regression Analysis. Might be useful to have. There are some times where you want to actually include mathematical expressions on plots. Maybe you want to include, for some reason, the Greek letter beta on a plot, or you want to include a hat character on top of a Y as a, let's say, in a title for a plot. And the way that you can do that in R is through using the expression function. So let's say that I do a simple plot here. Do this. Let's see that real fast. So I do a simple plot of college GPA versus high school GPA, and let's say on my plot I want, for some reason, in the main title, I want to have the Greek letter alpha for some odd reason. All I need to do that is to say expression, parentheses, alpha, in parentheses, and I highlight the code and run it. You see the Greek letter alpha is on my plot. There's a whole bunch of other things that you can do with this expression function. We don't have time to go into all of it. I'm not going to require you to put special mathematical characters like I have here on this example in the notes on your plot, but sometimes it's nice to know how to do that. I do encourage you to try to do that. And one way to learn more about the expression function and how it works is to issue demo plot math at a command prompt, and you will see a whole bunch of stuff that comes up that gives you examples how to do it. Last time we had a question about, well, how can I specify certain tick marks for my x-axis? Here's a demonstration of how you can do that. Let's say that I do a simple scatter plot again. And so this is exactly the same code that we had seen last time, except for I've added one little additional argument here. X AXT equal N. That stands for x-axis tick mark. And when I say no, N for N there, that means no. I don't want any tick marks on my x-axis. So if I simply copy and paste this into R, you see there's my scatter plot again, but nothing on the x-axis. Well, how do I put then stuff on the x-axis? Well, that's where I can specify, that's where I can specify the axis function. Now, on a plot, there are typically 4 sides to it in terms of the bottom x-axis, the top x-axis, the left y-axis, the right y-axis. And R simply numbers them, so the bottom x-axis is referred to as side equal 1. So if I say side equal 1, and then let's say I want to draw tick marks at 0, 0.5, 1, 1.5, and so on. What I could do is simply combine those numbers using the C function, as we have seen before. Or alternatively, I think I mentioned this last time as well, I can use the SEQ function, standing for sequence. I want a sequence of numbers from 0 to 4.5 by 0.5. So for example, there's my sequence. And, sorry, I keep on going back to the wrong one. And if I actually highlight that, paste it, now you see I have my nice little tick marks. Well, and like I said, it's a common question that typically students ask. Well, how do I control exactly what appears on the x-axis in terms of the tick marks? Now, these are often referred to as major tick marks in a variety of software packages. Let's say I want minor tick marks. So let's say I want ticks between 0 and 0.5 by 0.1. How would I do that? Well, that's where I can specify again using the axis function, side equal 1. I want to draw my minor tick marks at 0 to 0.45 by 0.1 now. The size of the tick mark, I'm going to control this to be 0.01. And in terms of its length, I believe that would be 0.01 centimeters by default. And then labels equal false, meaning don't actually draw the numbers in there, corresponding to every tick mark. And now you can see I've added nice little tick marks. Okay? So some of you, if you have a lot of experience with Excel, and that's most people, you might be wondering, why don't we just simply use Excel to do our regression analysis? Well, the stuff that we're doing in Chapter 1 and 2, yeah, you could probably get away with doing that. But please note that there are computational errors associated with Excel that have been well documented in the statistical literature, and I would assume probably other literatures as well. In fact, if you want to, you can see an older reference that I have listed here from 2005. But also, Excel, is only set for simple stuff. If I want to do more complex stuff, like what we're going to do in this class, you need to use a statistical software package. So that's why we don't use Excel here. Also, to hit on something that I mentioned before, you may, hopefully you remember from last time, when I type summary mod.fit, I get a different result from if I were to type summary GPA. And the reason being is because R always looks at the class of an object to decide how it's going to invoke the corresponding function. So in this particular case, the class of GPA is data.frame, and the class of mod.fit is LM. So summary itself is referred to as a generic function in R's terminology. And a generic function always looks at the class of the object, and then based upon that class, it will try to find a corresponding, what are called method function, to actually implement So notice how I get exactly the same results by using that method function. Now the reason why I bring this up, and why I talked about one reason before, was with regards to where you look for help for a particular function. But another reason why I bring this up is that you can actually see all the method functions corresponding to a different class. So if I say methods class equal LM, you're going to see a whole bunch of functions that pop up, including summary.lm, which will be actually executed, and when I did summary and mod.fit. But you see a whole bunch of other ones here. Now, we've already basically talked about mainly one so far. But as we go through the semester, we're going to talk about confint, we're going to talk about ANOVA, we're going to talk about DF beta. And so you might put a little note in your notes to come back here at some point, and this will help you see which functions are available to you. If you want to see also all the method functions associated with a particular generic function name, say methods generic.function equals summary, you see all the method summary functions such as summary.lm and summary.data.frame that we've seen before. Okay. Any questions? Some additional notes then. Maybe more so outside this class if you find out that you like R and want to learn more about how to use it. I recommend subscribing to the R listserv. This is a quite active listserv, over 100 posts per day. But also it's very useful to find help, because if you have a question about how to do something in R, probably somebody else already has. And you can search the archives of this listserv to find, hopefully, an answer to your question. Note that the link here, I forgot to update it, and that one does not work as well as, at least that search way does not work as well as one would like. So instead what you could do is go to chrismiller.com and click on links to stat resources. And down here I have a whole bunch of links regarding R. In particular, the listserv website and a search web page. And you can search the R archives by clicking on this searchable archives. And so, for example, if you typed in my name, you will see some stuff that I have posted there in the past. But you can type regression, and stuff will pop up for regression as well. If you like to read blogs, my favorite blog regarding R is the one that's listed there. This is published by Revolution Analytics. This is a company that actually sells R. Now you might be wondering, well, why would someone want to buy R? Because R is free. Well, the reason being is because there are companies out there that are using R, and who are they going to call if something goes wrong? Well, there's not a company that owns R, so who are they going to call? Well, what they do is often they will actually buy a version of R from Revolution Analytics. This company, for example, actually adds some stuff onto R itself, and then they'll give Revolution Analytics a call up. There are other companies like that have now formed as well. Kind of an interesting business model. Some of you who have some experience with stat packages before coming here, you might be thinking to yourself, well, geez, all I've done in the past was some point-and-click stuff to do statistics. I didn't have to write code. What are we doing here? Well, in order to do, a comprehensive statistical analysis, in order to learn about statistics, in all stat courses in a Department of Statistics across the country, across the world, you're going to do programming. But there are ways that you can use R in a more point-and-click manner. Let me demonstrate real briefly. There is a package in R called R Commander, or it's actually abbreviated as RMCDR when you install it. So if I say it's already installed on my computer, so if I say library package equal RMCDR, there we go. Up will pop up a nice little window that I can do stuff with. In particular, how about I tell this R commander the particular data set I want to analyze. So I can click on No Active Data Set, choose GPA, which we've already looked at before. And let's say I want to estimate my sample regression model. So I say Statistics, Fit Models, Linear Regression, response variable, call it GPA, explanatory variable, or what we've called a predictor variable, high school GPA. Click OK, and there we go. Sorry, I know it's kind of small there. I don't know if there's a way that I can increase the size. At least I don't see a quick way that I can increase the size here. But if you can't see it, what I will tell you is that basically we have the same output there that we had before. And in fact, up here, this is exactly the same code that we were using before to estimate the model. Notice it put the results into an object called Reg Model 1.1. That's just what it chose. And said Summary Reg Model 1.1 to generate that output. So you're welcome to use this if you want. But always in your projects, though, I want to see the corresponding code. And, of course, I want to make sure that the code runs. Because if I try to run your code and it doesn't work, well, that's not good for you, unfortunately. But one of the main reasons why I bring this up is that for those of you who are new to using R, this is also another way that you can learn about how to use R, because the code is given to you. So it's a nice little tool. Any questions? No, for some reason here, and probably I assume in your printed copy, or the copy you downloaded, for some reason when I was doing some copy and pasting when I was updating my notes over the summer, I for some reason didn't delete some stuff out. So you can delete all that out. And I give some other examples as well with R Commander in here too. Okay, so that takes us to page 152. What I would like to do next then is talk about the project. So if you could please take that out. So again, you can work in groups of up to 3 people on the project. I do recommend that you do that, but you're not required to. It's a group. I'm always afraid I'm going to trip over this. I really wish wireless webcams were more prevalent. At least when I bought that one 1 or 2 years ago, I couldn't find a good wireless webcam because that would make it a lot easier. I could put the webcam wherever I want to in the room, and I wouldn't have to worry about tripping over a cord. Okay. So also, this is due at class time on Tuesday, September 11th. Please email your completed project to me. If you're working in a group, you only need to email me one version for your entire group. But of course, put all the names of the group members in the actual Word file. In addition, please have the file name correspond to all the group members so that I don't get 10 to 20 different documents that all are the same name, project1web.docx. Okay. So this is just to kind of get you going with R here. It's not difficult. And what we have here for a data set is it looks at the presence of chemicals in cheddar cheese and how it affects its taste. I actually found this data simply at a website called Dazzle. DASL stands for the Data and Story Library. If you know, there's some STET students in here. If you who are TAs, this is a great source to go to for data sets that you can use for examples with your students. And so if you want to know more about this data set, you can take a look at that little web page set up for the data set. But typically with cheese, well, like cheddar cheeses, they're aged over time, and certain things happen to the cheeses; they're aged over time. And what we're looking at with this particular data set is some kind of measure of taste given by some taste testers. And the higher, the better the taste. And we look at the presence of acetic acid, hydrogen sulfide, and lactic acid in the cheese. And there's a total of 30 different cheeses that we have data for in this particular data set. So sample size is 30. For this particular project, we are only going to look at taste as the response variable and acetic acid as the predictor variable. So we want to know, well, what happens to the taste as acetic acid goes up or it goes down? Okay. So part A here, and also I should mention, that I actually give you the code of how to read in the data into R. This is from my own computer itself, so of course you will need to change the location of the physical address of that particular file. It's an Excel file. You can find it from the project's website of the course. The project's webpage of the course website. Have we talked about the head function before in this class? I don't remember. Okay. And so what I did, this is just a quick way to kind of verify that I read it in correctly. I use what's called the head function to look at what's by default the first 6 observations, just to make sure I did it. If I want to look at the last 6, I can use what's called the tail function. Or you can simply just type cheese and you get the whole thing. I mean, 30 observations, you could do that. Just I didn't want to take up all that space here in my project. Any questions about the data? Yes?
Yes, I don't understand the way you read it.
You don't understand the way I read it?
Yeah, I read it back then, the data.
We looked at an example just like this last time with the high school and college GPA data set. There was an Excel version of that file, and basically it's the same code. Okay? Sorry if that wasn't clear. Any other questions? Yes?
That means that you have to put information in the website and copy and paste in Excel?
Nope, nope. You go to my website, you download the file, put it on your hard drive, someplace where you know where it's located, put in the address on your hard drive where it's located in that ODDC Connect XL,
Yeah.
and that allow you to read it. Okay?
Website, yeah.
So, okay. So now part A, construct a scatter plot of taste and acetic acid. Interpret the relationship between the variables using the plot. Why don't we do that right now in class, just to demonstrate what I'm expecting for you to turn in for each of these parts. So, again, I guess just for demonstration purposes, I can go to my project's webpage. I can right-click on the file, save target as, download it to my computer. And over here, find this. What I've done is just copy and paste the code that I had in the Word document, where now I've changed the actual location for where the file is stored to where it is actually on my hard drive. I run the code, and there's my data. Okay, now I need to actually do the plot. So, how do I do a scatter plot? Well, we learned about the plot function last time. So, x-axis, I'm going to take the acetic variable out of cheese. For y-axis, I'm going to take the taste variable out of cheese. Let's see now, I'm going to put x-axis title, y-axis title, and so on. Put some grid lines on it. Run that, and there's my plot. So, what do you need to then turn into me? Well, I want to see all your code that was used leading up to that point. So copy that code. Close this out. Come into my Word document itself. Paste the code. Now note how things over here for this data set, they're not really lined up very well. That's because by default I'm using an Arial font, and every character is not necessarily exactly the same width. So what I would like you to do is actually change that font then to something that has a fixed width, like Courier. Okay? Notice how everything's nicely lined up now. Also, I need to do some other stuff to make this look nice. So for example, notice here I have this line of code, then I have this long address that's just kind of dropping off to the end of the line. So why don't we just break it and then indent to signify that indeed that the code is continuing for that particular line. Also, you see a similar thing happening here for plot. So we're going to just move that in. Oops. Notice also I have a little plus sign there. Well, why did that occur? Let me come back here. Notice that in this line of code, it got to a point where R reached its maximum width. And then it says, okay, you want to continue the code to the next line, so I'm going to put a plus there to say, okay, I'll continue it to the next line, and then it continues to enter. Well, I don't need to see that plus. And in fact, it's kind of a pain for me to deal with those pluses, because when I run your code then, R will interpret that plus to mean something else, like add. Okay? So I just simply delete that. I got a blank line here. I can delete that too. And now my code's in a point that is, in the right format of what I want to see for your code in output. Next, I need to get the plot into into Word. So I just come over here, copy to clipboard as meta file, right here. And the plot's kind of big. Why don't we just make it a little bit smaller? So I just make it smaller as you would any kind of picture in Word. And now I need to complete this problem. It says interpret the relationship between the variables using the plot. So I can say something like this. As acetic acid increases, taste tends to increase as well. And now I'm done. So that's what I'm looking for when you answer problems on this project. Are there any questions?
When we send it to you, do you want us to do it like it is there, like just cut and paste it into the...
That will be the easiest.
Okay.
Otherwise then you're creating a whole new Word document and maybe retyping something. There's no reason to.
Okay.
Yeah.
Any reason why we would copy the code from output window instead of the editor?
The reason being is because I want to see your code as it is run in R. Now in this particular case it's not as big of a deal, but in other cases it's going to help me diagnose maybe things that you did wrong. So that's why I want to see as it's executed.
And when we send it to you, we just leave the file location as it is on our computer.
Yeah, that's fine. I mean, if you don't know where it will be located on my computer. Or maybe if you did, then we need to talk about that. Why would you know that? Other questions? So I know this is a little picky, but there's a number of reasons for it, and that is, first of all, it looks a little bit nicer. I've graded lots and lots and lots of stuff in the past, and when people use different fonts and stuff, or they don't go back and edit their code at all, it just looks like a big mess. It's hard for me to find stuff. Second, if you look at any book that's on R, typically you will see this format. Not all books, but typically you will see this particular format. Okay, so this is not just something I came up with myself. One other thing that might make your life easier too. Does anyone know about styles in Word? A few. Well, all of you are grad students, and all of you are going to be, typing some kind of thesis or dissertation or something like that. And if you do it in Word, I strongly recommend that you learn about styles. What a style basically is, it's basically a style of font or width between lines in a particular paragraph that you are using. So for example, the default style is always in Word called normal. Well, I've set up my own style in Word called R. So let me go ahead and copy and paste this code and output again to show you what happens when I use a style. Okay, so if I highlight that code, come over here to the style that I've created, look what happens. It's almost completely formatted the way I want it to be. How do you create a style? Well, let me come up here to Styles, and let's see, come down here for New Style, and let's give it a name. Let's say R2. Not for R2D2, but since I already have one called R. And I can come here for formatting. Let's say Courier. Maybe I want size 10 just to be different. I can come down here to Format Paragraph. If, let's say, I don't need it in this case, but let's say you're doing something else. You could change it to double spaced or exactly a certain line spacing. You can change indenting. You can do a whole bunch of stuff. What other ones are good? Yeah, those are the main ones that you need to know for this class. And if I just click OK, now I have a style called R2. And unfortunately, it automatically converted this to R2 because that's where it was located when I was creating my style. So I can come back here and do that, and now it disappears. So that's how you can create your own style. Any questions? Any other questions? Okay.
This question?
Yeah.
Yes, the case is 1 to 6. You did that on purpose. Like it says
The head function, you mean this right here? The head function by default will always show the first 6 observations.
Always.
Always. The way that you can change or look at something different. So here's head cheese. If I do head cheese again, n equal, let's say 3. There we go. So just look up the help for head and you can see it. Other questions?
We have to work on this 6 number or the total information for this?
All of the data set.
All of it.
Yeah, as I tried to say earlier, I'm only showing you the first 6 there because I didn't want to print off all 30. Obviously, after you read in your data, you want to make sure that it read in correctly. And one quick way to kind of confirm that is to look at the head function or the tail function with respect to your data.
And the library is only one time. You have to repeat the library RODBC and again and again.
Yeah, I mean, this was mentioned last time. You only need to do library ODBC once, whenever R is open. Okay? If you're to close out R, you need to do it again.
Yeah.
Let's continue then looking at the project. Okay, so part B, as you might expect, let's use the LM function and find the sample regression model. So what are you going to do? Use the LM function, do summary of whatever you get from the LM function, copy and paste that code into the Word document, and then actually state the regression model correctly. So if you say your model is something like, let's say y is equal to, I don't remember what B0 is, I'll just say 2 plus 3 times x, that will be wrong. Because you need a hat on top of y. You need to make sure you use the proper notation. Because how am I supposed to know that that is the estimated value of y versus the true value of y? That's why you need a hat on top of that. Also, if you say y there and you use an x as well. Well, what is y? What is x? Well, you need to define it. X is acetic acid, y is taste. Alternatively, you can say taste is equal to 2 plus 3 times acidic. But if you do that, you still need to put a hat on top of taste. So at least for me, I use the math type equation editor. So I would say I would do something like this. Oops. You can use the equation editor that already comes in Word. Let's see. So I just come here, find the corresponding thing that will allow me to do a hat on top of it, and there we go. Obviously, I would use a different font size, but that's how I would do it. Any questions? So you do need to use proper notation. Part C, interpret the relationship between the variables using the regression model from Part B. Well, tell me what the model's saying. Is it saying that as acetic acid increases, taste goes up, or does it go down? Remember how we interpreted that sales and advertising example, how we interpreted the model in that case. For every 1 unit that advertising went up, how much do I predict sales to go up? Same thing here. Part D, program into R the formulas for B0 and B1 and verify that indeed that R is doing the calculations correctly. We haven't done this particular thing in class yet. For the sales and advertising example, I showed you how you could go through the calculations by hand. Now what I want you to do is program in the formula for B0 and B1 into R to verify indeed you get the exact same thing. So you're going to need to figure out, well, how do I do a sum in R? Well, there's a sum function. Part E, well, let's actually plot the sample regression model on the scatter plot that you did before. Now the remainder of this project right here corresponds to stuff that we'll do at the beginning of Chapter 2. So I'm not going to discuss this at this time. But lastly, I will discuss the extra credit. Now hopefully, outside of this class, in your very first stat class, your professor showed you how you could simulate data. Simulate data from like a normal distribution. Well, what I want you to do, and this is for extra credits, so you don't have to, is to simulate a sample size of n equal 30 from the sample regression model that you found in Part 1. Use a C number of 7172. Okay. Let's briefly talk about random number generation in R. So when we were looking at the help for, I think it was the p-norm function 1 week ago, we also came across a function called R-norm. R-norm stands for random normal. If I want to simulate data from a normal distribution, all I need to do is say R-norm n equal, let's say 30, mean equal, let's just do a standard normal, mean equals 0, SD equal 1, and that's what I get. So if I did a histogram of that data, it should look kind of symmetric, mound-shaped, like a normal distribution. Well, let's say I do the exactly the same thing again. Now I get different data. Why did I get different data?
Random.
It's random. So if I want to reproduce the exact same data that I simulated, I need to what's called set a seed. I'm not going to get into the details of random number generation here, other than you can set a seed, what's called a seed number in R. Seed numbers exist in all stat packages, exist in Excel too. Set.seed, what's seed number? 7172. So that now, when I use this R-norm function, this is what I get. And let's repeat the exact same set of commands, and I get exactly the same thing again. So, seed numbers help you reproduce the exact same result. With that as background, I want you to figure out how you could simulate data with respect to that sample regression model. that you would find in Part B. I'm not going to tell you any more about how to do it, though. That's why it's extra credit. Okay, are there any questions? Okay, so that is project number 1. Again, it's due Tuesday, September 11th. So I guess 12 days from today. Okay, let's see. So we left off on page 152. So our population regression model. So this is what we are saying the relationship is between x and y in the population itself. Is y is equal to beta 0 plus beta 1 times x plus epsilon. This epsilon is what's called a random error term. So for every element in the population, there is an associated epsilon to it. If you somehow knew all the epsilons, and you plotted in all these epsilons in a histogram, again, the histogram should look like a normal distribution in terms of its shape. Well, that normal distribution is dependent upon a particular parameter, sigma squared. So our model here actually has 3 different parameters, beta 0, beta 1. We've talked about how to estimate those so far, but also has sigma squared. I'd like to know what that is too. Well, what does sigma squared measure? Well, just to review, here's one of the this little diagram that we saw the second day of class. So we have a population of 6 xy values, denoted by the green dots on that graph. And the red line there is expected value of y is equal to beta 0 plus beta 1 times x. The distance between the green dot and the red line is our epsilon. The variability of these green dots from that red line is represented by this sigma squared. And what we talked about before was that as these green dots get closer and closer to the line, sigma squared does what? Goes down, because there's less variability around the line. As the green dots get farther and farther from the line, or there's more variability around that line, sigma squared goes up. Okay? You probably like to estimate that then. You like to know, well, how are these points varying around that line? So how can we estimate it? Well, that's where the residuals come in. So we also took a look at this plot in the past too. The yellow dots here represent the actual values in the population that were sampled. So there happened to be a sample size of 4. And we estimate our model. So we get a sample regression model that's denoted by blue. The distance that the blue line is from the yellow dots is our residual. So you can kind of see that that distance kind of is playing the same kind of role as the distance that we were seeing between the green dots and the red line. So it kind of makes sense then, well, why don't we use then this particular distance that we see here as a way to maybe help us measure the variability. In other words, to estimate sigma squared. So this distance is y hat, which basically gives us the line, minus the actual observed value of y that we had in our sample. So we're going to use those distances. Well, how do we use the distances? Well, we use them in the same way as you did in your very first stat course when you're finding a regular old sample variance. So in your first stat course, you learned about, it's often denoted by s squared. Maybe use different notation, but this is the most common. And if I just simply had a sample of, let's say, y values, and I look at the distance that y is from now the sample mean, I square them, and then to get an average value of these squared distances, I divide by n minus 1. This is called my sample variance. Why do we have an n minus 1 there versus n? Does anyone remember? Because your professor said that's what you're going to use. It has to deal with the degrees of freedom, exactly. What we would prefer to use here instead of y bar, we would prefer to use mu, right? If we somehow knew it, if mu was, let's say, the mean, the population mean, we like to use that. But don't know what that is, so we replace by something that's estimated. And what ends up happening then, that causes you to use n minus 1 there instead. Rather than having, let's say, a degrees of freedom of n, basically being your sample size, now it's n minus 1 due to this estimated value, without going into all the details of degrees of freedom. Well, now, what we're going to do here to estimate our sigma squared that we have for our regression model, we're going to basically do the same thing. Instead of having y bar, we're going to use y hat instead. Okay? But we're still going to square them, these differences, add them all up, and now we're going to divide by n minus 2 rather than n minus 1. The reason being is because before we only had one thing that we had to estimate. We had to estimate mu. Now we have to estimate beta 0 and beta 1. So we lose 2 degrees of freedom. Essentially, I know degrees of freedom is often a tough concept for beginning students in statistics to understand. Essentially what this means is that if you knew what B0 and you knew what B1 was and you knew n minus 2 of your observations, you could figure out what the other 2 observations are. That's essentially what degrees of freedom are in that kind of a context. So this is my estimate of sigma squared. The name of that estimate is called mean square error. Notice we are squaring errors. In other words, the distance that the line is from the actual point. We're squaring these errors, and then by dividing by n minus 2, it's like taking a mean, sort of. So that's where the name comes from. Now notice here in this numerator, let me do some erasing, and we'll abbreviate mean square error with MSE. Notice here in the numerator we have something that is something we've seen before called SSE, sum of squared errors, which is just the sum of the y minus y hats squared. What we saw before when we were talking about the least squares method. So here's a question then, and hopefully it's not too difficult, just to make sure you're following this. So I have 2 plots here, 2 different samples. I plotted x, I plotted y. These plots are constructed in a particular way such that I always have the same value of x in both the first sample and the second sample, just different values of y. The regression models are exactly the same, plotted there as well. Which plot is going to have a higher MSE, plot 1 or plot 2? 2. Okay. Simply, that's how MSE works. Well, let's look at a more, let's say, practical interpretation of what MSE means in the context of one of these plots. Again, hopefully, in your very first stat course, a professor talked about something such as something called the empirical rule, or something called Chebyshev's theorem. Does that sound familiar? If you took my 801 class, yes. Review the videos. Anyway, well, rather than talk about empirical rule and Chebyshev's theorem, instead what I more often do in a Stat 801 kind of class is talk about what I call a rule of thumb for the number of standard deviations all data lies from its mean. In other words, all data in a data set should be plus or minus 2 or maybe up to 3 standard deviations away from the mean of all the, let's say, the numbers in your data. What that basically means is this, and this is the example that I use in a Stat 801-like setting. Let's say that you are very concerned about getting to this class on time every day. And so what you've done so far this semester for the 3 previous classes is that you've kept track on how many minutes it took you to get from home or your office or wherever you start off from. It took you how much you kept track of how long it took you to get here. And let's say the first day it took you 6 minutes. The next time it took you 4 minutes. And then last Tuesday it took you 5 minutes. Okay? Well, what's the average? Well, let's call that average x bar. The average is 5, if you do the math. What's the standard deviation? Quick, someone do the math. Oh, come on, it's 1. So the standard deviation is 1. So what this rule of thumb basically says is that I should expect all my times for how long it takes me to get to class every day to be between to be 5 plus or minus 2 times 1, or in other words, 3 to 7. So if class starts at 11 a.m., if you wanted to pretty much guarantee that you're going to get to class on time every day, what time do you think you should leave your office or your home? Probably 10:53. Okay? I just subtract 7 minutes from 11 o'clock. So what this rule of thumb is basically saying that, all your time that it takes should always be between these two numbers, generally speaking. Now there's probably going to be some outliers. Maybe if you're driving your car and there's a car accident on your way to school, okay, I'll give you a pass if you get to school late that day. But this is how that rule of thumb works. But how can we use this rule of thumb then in the context of regression analysis? Well, y hat is now going to play the role of the mean. What plays the role of the standard deviation is, well, the square root of MSE. So that I should expect all y values in my data set for a particular x, again, for a particular x, to be between y hat plus or minus 2 times the square root of MSE. Let's see if that happens with our 2 previous data sets that we looked at in class. So here's my sales and advertising data set. For advertising of 1, I had a sales of 1. We have already calculated y hat before. We've already calculated the residuals before as well. Now I create a new column that contains the squared residuals. I add them all up, I get 1.1. So to find MSE, I take 1.1 divided by 5 minus 2, and I get 0.3667. Take 2 times the square root of MSE, you get 1.211. So that, for example, if x was equal to 4, my y hat plus or minus 2 times the square root of MSE is about 1.5 to 3.9. And I've even plotted it here. I did a very simple plot. So here is about 1.5, and here's about 3.9. And you can see that we happen to have one observation at x equal 4, and it falls between those 2 outer limits. So what this rule of thumb gives you is it gives you an idea of how much you should expect the points to be around the sample model. How far from the line. Let's look at another example. This is the high school and college GPA data set. Suppose I have the results from using the LM function in mod.fit, like what we've done before. So summary in mod.fit. To find the MSE in the output, you need to look right here. This says residual standard error. What that means is actually the square root of MSE, which is 0.297. So why is R using that name? Well, MSE means square error. Error is just another word for residual. So that's where the residual comes from. Well, why standard error then? Well, where that comes about is that, and hopefully you saw this in another class, is that if you were to take the square root of the variance of some statistic, often that's referred to as a standard error. Just statisticians decided to start using different terminology to confuse new students to statistics. And so that's referred to as a standard error. So by me taking the square root of MSE, that's where the name standard error comes from. Okay. So MSE then would be the square of that, 0.297, and you get 0.088. Well, how if I do the same kind of plot that we did before? What I've done here is for every x in my data set, I went y hat plus or minus 2 times the square root of MSE, and this is what I get. Notice all the points are within those outer boundaries, as we would expect given this rule of thumb. I simply did this plot in Excel. You can do it in R too. Any idea of how you would do it in R? So basically what I need to do is draw a line segment from a bottom number to a top number. So I want to draw a line segment here. So what function do you think will be very helpful in R? Not AB line, because AB line will actually extend the line throughout the entire plot. But it was a function we talked about right after AB line. Segments. Yeah. That's all. So try that on your own. Well, how could I get then this value of MSE into an object? Well, you could just simply say MSE gets say MSE gets 0.297 squared. You could do that. But oftentimes you want to automate the process of how can I get this 0.297 to an object that I can maybe do other stuff with, because we will use this MSE a lot throughout the semester. So what you could do, here's 2 ways. First of all, you can just kind of calculate MSE yourself. It's not that difficult. We've looked at this before. If I did names of mod.fit, one of the components is something called residuals. If you did mod.fit $residuals, you get all the residuals. The E sub I is in our notation. So how about you just simply sum all the squared residuals? You need to divide by n minus 2. Well, guess what? There's an element of mod.fit called df, or degrees of freedom, dot residual, that gives you your n minus 2. So that's one way. Second way, what I could do in R is instead of just simply saying summary mod.fit, how about I put the results from summary.fit into an object? Call it whatever you want. I say summary.fit. And if you say names of summary.fit, again, just like what we did with mod.fit, you can see what information is actually in there. In particular, there's one called sigma. That is the square root of MSE. So if I want to pull sigma out of the summary.fit, just like what I did before with mod.fit, I say summary.fit $sigma. And I get the square root of MSE. Any questions? Okay, let's move on. So the last 2 pages of this chapter just kind of reinforces what some of these underlying assumptions of our model mean. So we looked at these assumptions, I think, the first or second day of class. Again, our population regression model is y is equal to beta 0 plus beta 1 times x plus epsilon, where epsilon is distributed independent, normal, sigma squared. Okay? Well, what one can show, and we talked about this a little bit before, is that the expected value of y is beta 0 plus beta 1 times x. You could actually do a very little mathematical proof of that. So what this is saying is that given particular x, I would expect on average the corresponding y to be beta 0 plus beta 1 times x. This is an assumption for my model. Why not have, let's say, maybe x squared in there instead? Or maybe instead having x raised to the beta 1 power instead. Well, you learn about x to the beta 1, how to handle that in a course called nonlinear regression. If you had, let's say, x squared in there instead, well, we'll talk about that starting in chapter 3. So there's a variety of different kinds of models you can have out there. We're talking about pretty much the simplest one. Also, what one could do is show then that the variance of y is equal to sigma squared. How does one do that? Well, as follows. Here's variance of y, and if I put in what y is inside of here, note that beta 0, beta 1, and x are all constants. What's the variance of a constant like the number 3? 0. Okay, so those fall out. The only thing that you're concerned with is epsilon. And well, what is that? Right there. Sigma squared. Sorry, my line wasn't a straight line. I didn't take the most direct route, but that's where that comes from. So variance of y is equal to sigma squared. So what does that mean then? Well, this puts into a little bit more context what that rule of thumb that I was just talking about actually means. In your first stat course, you did stuff like this. Let's say that Z has a standard normal distribution, mean 0, variance of 1. And you often spend some time finding probabilities, such as what's the probability that Z is between -2 and +2? Hopefully that looks familiar. Well, typically the way you would find that is first break this up into the probability Z is less than 2 minus the probability Z is less than -2. And then hopefully your professor did not use a standard normal table. Instead, they would have used R or some other stat package, and they would have used something like this: P norm Q equal 2, mean equals 0, standard deviation equal 1, minus P norm, but now I put a -2 in there, and I get 0.95, about 95%. So that's the probability being between 2 standard deviations away from the mean. Well, what we can do then is say, well, in our particular case, for a particular x, my mean is expected value of y, my standard deviation, sigma, put a 2 in there as well, and guess what? It's like I'm out of ink here, my pen's not writing. Let's try this again. That's strange. Well, this is a new one. I can't write with my pen, but I can write with my mouse. It's like my pen is out of ink, which shouldn't really happen. And I get this probability of 0.95. Okay? So what that says, it basically is what we were seeing on those plots. That you expect, generally speaking, all your possible values of y to fall within plus or minus 2 standard deviations from the mean. Okay? Well, here's a little graph showing that aspect. This is in 3 dimensions. So I have a y-axis, I have an x-axis, and then, let's see if I can write now with my pen. Yes, I can. All right. You can think of then the z-axis coming up is like probability, like you would have for like a normal distribution when you're looking at the normal distribution plotted. And here's my population regression model written in terms of expected value of y. And what that's saying is basically at every possible value of x, you can think of having a normal distribution. And generally speaking, you expect about 95% of all your corresponding values of y, if I were to project this over to the y-axis, to fall within those 2 numbers. That's what the assumptions of our model are saying.
Shouldn't it be slightly amended because of the use of freedom of the sample for each x?
No. And are you worried about using a t distribution rather than a normal distribution? A t distribution is not used yet. Okay, the t distribution is not applicable to this what I'm talking about here. Where it comes about is when you're talking about what are called sampling distributions for statistics. And we'll start doing that in Chapter 2. But no, this model assumes normality. So t distribution doesn't apply.
When you calculate the 95% confidence
I'm not doing a confidence interval.
basic.
No, I'm showing you what this models assume. 95% of the time, you should have value between there. This is going to be related, and I think this is what you're getting at, related to a confidence interval for the expected value of y, yes. But when we do that confidence interval, we don't know what beta 0 and beta 1 are. So we replace them with their estimates, and guess what happens then? This normal distribution that we were working with, Now we're going to start working with the t-distribution. Just like in your very first stat course when you were doing a hypothesis test for mu, often you've talked about the normal distribution case first, and then you realize, okay, I'm not going to know what sigma squared is, so I always have to replace it with s squared, and you go to a t-distribution.
Yeah, I understand. In your case, you basically have an estimate of the line.
I'm not dealing with estimates here at all.
Okay.
These are, I'm assuming that beta 0 and beta 1 are known. Okay? Other questions? Okay, why don't you take out your chapter 2 notes and let's move on. Or we can just end it there. Why don't we end it there? Okay, that's it for today.
No, I have a